Welcome, everyone. Today we have the pleasure of having Nadia Dachlythra with us. She comes from the Stockholm University in Sweden, and she will talk to us about CMB instrumentation. Nadia started her career with her degree from the University of Athens. Then got a master's degree from Copenhagen, and she liked the Nordic climate so much, so she decided to stay. And now she's finishing PhD. She's finishing her PhD at Stockholm University. Nadia, the floor is yours. Thank you for coming.
Okay, so thank you for the introduction, and thank you very much for the invitation. I'm really happy to be here today. So for my PhD, I worked on modeling optical systematics for cosmic microwave background telescopes, but I don't really work in the lab. I'm not doing hardware. Instead, I work on the software side of things. And I'd like to take a couple of minutes to explain what my field is about. So when we deploy, when we want to suggest an experiment, a bunch of capable people put their heads together and they write down a proposal and they address that to the funding committees. And they say, look, we need to build this new instrument because it's important for this and this and that reason, and it will help us develop our understanding as a community and so on. But ultimately, the statement needs to be quantified in terms of the scientific goal we want to achieve with this instrument. And in the case of CMB telescopes, one of the main goals is to constrain the so-called tensor-to-scalar ratio parameter, which we will talk about in a bit. Let's call it the parameter R, and constrain that parameter with some accuracy X. And there's a number of factors that can go wrong and threaten this accuracy that we want to achieve. Some of them come from the signal that we measure from the sky. If we knew exactly what we were going to measure, we wouldn't need to build instruments in the first place. But some other factors come from the instrument itself. So, we might have a bunch of money and manpower invested into building robust instruments, but there is no reason and no sense in trying to prevent all the problems that will arise, because they will arise because we work in real conditions. But instead, what we can do is that we try to model the impact that these problems will have on our endgame, which is, in this case, in my example, the parameter R. So what we do when we work on the software side of things, we code up our instrument to the best of our abilities, the basic functionalities of our instrument, and we're trying to approach a realistic scenario. And then we simulate the mission. So the scan strategy that we will follow, the calibration runs and so on, and then we run the cosmological analysis on the simulated data, all the way to the parameter that we want to constrain, to our endgame. And we call this the baseline case. And in this baseline case, we assume that we know everything perfectly about our instrument, and we have some priors about what to expect from the sky because there have been microwave instruments in the past. And this is our baseline case. And then we go and start perturbing all the slated factors that went into the instrumentation software. So let's say, for example, I have one surface of my telescope that I expect to be fully absorbed, because I don't want any stray light going around in my telescope messing up with the signal. But let's say that in reality, this is only 95% absorbed, this black surface. So what I do is that I perturb this parameter, and then I run my simulations again, all the way to the end parameter that I want to constrain, and I see how much of an error this particular effect causes to the accuracy of my desired parameter. So I do that for every little problem that can arise for the instrument, and then we construct what we call a total error budget for the instrument. So effectively, you see your instrument as a little interactive map, and you say, okay, this component A of my optical setup is allowed to contribute 5% of the total error budget. This component B might be a little bit more quirky, so it can go up to 10%. And then together, working with the hardware people, you can get a better understanding of your instrument in total and try to safe-proof your cosmological analysis. And I hope this will get a little bit more clear as I go through the slides. I work mostly on characterizing, doing some beam modeling for the Science Observatory, but I will not go into these technicalities. I don't think it's the interest of most people here, but I will try to give a little bit of a more pedagogical talk about the importance of beam modeling and what we do in the CMB community about that. So the CMB community is in fact very, very wide. We have had a bunch of experiments taking place in the past and powerful missions that are going to take place in the future. We have had deployed satellites to observe the microwave sky, such as COBE, which was the first satellite back in 1989. Some of the chronologies might be a tiny bit off. I usually relate to the initial deployment dates, kind of, but this is pretty much in line with the history. We had other satellites such as WMO. We had Planck with 3 powerful releases in 2015, 2015, and 2018, introducing us somewhat to the era of precision cosmology. We have had balloon experiments as well, such as Boomerang and Spider. And those are easier to construct and cheaper to construct in general, but they come with other limitations. And we have also observed the microwave sky from the ground with BICEP, with ABS, and I'm listing here only a few of the experiments that have taken place because there are many, many more. Now, we have the Simons Observatory, large and small aperture telescopes, which is what I have spent most of my PhD time working on. And those are going to be deployed very soon. We expect the first flight early 2024. And we have powerful missions in the future. Lightbird is a satellite, which is Lactose Neolithicus mission, is going to be deployed at some point after 230 or 235. I guess I'm not really clear on that. And then one more experiment that I left out, which is also going to be rather powerful. It's going to be a ground experiment. It's called the SIMBI Stage 4. And it will resemble somewhat the structure of the Simons Observatory telescopes. So one large aperture telescopes and many more small aperture telescopes. So it's a very exciting time to be a SIMBI scientist right now. And the reason that we put so much effort as a community is because we can get all sorts of information from the SIMBI. So if we take a step back, this is a very notoriously overused plot. But the reason that it remains as overused is that it serves as a great depiction of the history of the universe from the early times to the very times. So if we were to fast track this a little bit, because I'm sure most of you probably have seen, the bottom line is this. All the large-scale structure that we see today in the universe is sourced by vacuum fluctuations that were inflated. They see the density perturbations that then collapsed through gravity and formed galaxies, clusters, the most massive objects that we observe today with our telescopes. So at this time here, that the universe cooled down enough, the same photons were able to travel more freely because they were not getting constantly scattered by free electrons as those were binded into atoms. So we call this the last scattering surface, the point at which the same photons became sort of transparent to matter. And this occurred when the universe was about 380,000 years. So we want to look at this afterglow, as we call it here. And this has been beautifully projected, well, by many experiments, but I'm showing here from the Planck 2018 release, where we have the temperature anisotropies projected on the celestial sphere. We have mapped the microwave anisotropies on multiple angular scales. And then what we do is that we decompose these anisotropies with the spherical harmonics in order to construct the power spectrum on the multiple domain of the temperature anisotropies. And this has different structures at different multiples. So at the lower multiple region, we see this sort of scale invariant spectrum that resembles the density perturbation spectrum. We can get a lot of information for the initial conditions from this side of things. And then at the higher multiples, you have this characteristic acoustic peak structure that is formed due to the barium photon fluid oscillator. And so we can use the positions of these peaks and troughs and their amplitude to set constraints to infer cosmological parameters from them. We can do all sorts of things. We can use the higher end of the multiple range of the power spectrum, what we call the damping tail, to constrain the number of effective spaces. We can get an idea about the degree of primordial non-Gaussianity one can expect. And one goal that is very, very important into SIMBI science, which is to put an upper limit on the probability of primordial gravitational waves being present at very early times. And that would serve as a very strong probe for the inflationary scenario. So this exponential expansion of the universe that happened at the very beginning. And so all of these parameters cannot simply be inferred from the temperature anisotropies of the SIMBI. We also need the polarization anisotropies, the signal that is much, much fainter, and is a result of the Thomson scattering of the SIMBI photons by free electrons that had the quadrupolar pattern. So we're strictly talking about linear polarization. Typically, circular polarization is not expected at the SIMBI. It can be detected, however, as a result of other effects that took place between the last scattering surface and the time that the light reached our telescopes. Or it can be a result of more, say, exotic scenarios, photons such as action-like particles, but we're not going to look at that at all, simply linear polarization. And the good thing is that if we do our math right, we can actually break the linearly polarized part of the CMB into a strong parity even part that is curl-free, and we call modes. And this can be sourced both by scalar and tensor perturbations. And then a fainter part, which is parity-owned and divergence-free, and this can only be sourced by tensor perturbations. So we already have a very important distinction there. And we need to do this kind of tricks because the polarization isotropies are in fact almost 2 orders of magnitude fainter than the temperature isotropies. So we're looking at a very, very faint primordial signal that is threatened by various problems. And if you want to take a small visual aid about how this scheme of the B-modes would look like, I projected roughly as headless vectors here from the W-map collaboration on the celestial sphere with a nice with a nice background. Okay, so why do we care about the different origins of these two components of the polarized part? So the inflationary gravitational waves, the disruptions of space-time, they are essentially perturbations of the metric tensor that can be loosely thought as the generalization of the gravitational potential when we are in Newtonian gravitation. And so what we do is that we craft up this parameter that we call the tensor to scalar ratio, and we denote by R. And this is exactly what the name suggests. So we want to have the best estimation that we can of the amplitude of tensor perturbations that we detect versus the amplitude of all the scalar perturbations that we detect from the single signal. And of course, we already have constraints on that. We have had, as I showed, many experiments in the past, and we have some forecasted constraints involved. And the latest ones come from the bisescate collaboration in combination with the fourth release of the Planck data. And this has set an upper limit of 0.32 at a 95% confidence level from a publication back in 2022. And this actually came with an important consequence that I'm not going to go deep into because I don't have the expertise. But trusting these constraints suggested that there might be a whole class of inflationary models that is singled out. And if you were at any email threads or any journal clubs at the time, it was one of the most heated discussions about a paper that I have ever heard because the theorists believe their models and the data analysts are sort of trained to believe the data first, and it was quite interesting to follow these chats. So currently, for the ESO telescopes, we, as I said, it's quite common to express our scientific goals in terms of this R parameter through its statistical uncertainty. So for the ESO telescopes, we're trying to constrain them with an uncertainty that is smaller or equal to 0.003. ESO is the Simons Observatory one. I might say it a lot in the next slides. And for the power formations in the future, for the ground-based SIMBASE-4 and the light-burst satellite, those instruments, we want them to be built in a way to be able to detect a 0.003 value for the R parameter or larger with statistical uncertainty that is only 1/3 of this value. And now we haven't really detected tensor perturbations in that sense, but we have ways to visualize how this B-mode spectra would look like corresponding to some value of this expected tensor to scalar ratio. So this was a nice review that was written by Ichiro Komatsu only recently, and he was talking about the new physics that we can get from the polarized light of the CMB. So he's showing here the B-mode power spectrum, so the parity even part, the strong part of the linear polarization of the CMB, and the data points from experiments that have taken place in the past. And then we have what we would call the lens B-mode spectra. So essentially, E-modes masquerading as B-modes due to gravitational lensing of the CMB by various objects on its way traveling from telescopes. And so this is somewhat fake. This is just part of B-modes that have been mixed into the primordial signal we're looking at. So, and then if we have a tensor to scalar ratio of 0.03, which is in line with the upper limit that we have from Tristan Tal, then we would expect to see a B-mode spectrum that looks a little bit like this. So this is very faint, and we need to check that nothing else, no systematic noise, nothing leaks residuals above this value on a power spectrum. So to be able to say, okay, this is a detection, this is robust. So we have very, very ambitious goals looking for such a faint signal, and we need to be able to take care of all the problems that will arise. And that's going to be discretized into 3 main categories. We have the foregrounds that people here know much more about from me. So we have, this is the galactic dust sky map as it was published from one collaboration in 2015. And the galactic dust dominates in polarization in the very, not at the very the high end of the frequency spectrum that we're looking at for CMB. So you can see these beautiful contours here, and those are the molecules of the galactic field. And so I'm really scared to say this because there are many dust people here, so correct me if I'm wrong. But with the thermal dust emission, we basically have carbonaceous and silicon particles, and those, you know, they can and they will align their magnetic dipole moments with these field lines, and they will emit polarized light. And I hope this was a decent definition because I really like about it would be nice. And this map is for, you know, dust of a temperature of approximately 20 Kelvin. Now, in the lower frequencies, we have the synchrotron emission dominating, so cosmic ray electrons accelerated by magnetic fields. And if we were to plot the brightness of these foregrounds here, then you can see that the CMB is literally gasping for air around 90 gigahertz. So there are a couple of things that we can do about this. First of all, since we know the foregrounds have a different spectral energy distribution, they're frequency dependent as compared to CMB that is an almost black body. Then we can, you know, we just need more data points. We need to look at more frequencies to be able to model, not just, but the first thing that we can do is to look at more frequencies to try to model better this spectral energy distribution and thus separate the contaminants from the signal. So satellites such as LightBird will have up to 22 frequency bands of 20% with around frequency center each. So that's already too much. And of course, this is not easy to do, but that's why we're doing so much time to construct new experiments and getting so much funding to try to. And then the other thing that we can do is that we can try to deploy more detectors into this frequency range here, where we think that we can get better constraints for potential scalar ratio parameter. So for the Science Observatory telescopes, for example, we of course need to be able to look at all the frequency range to characterize more foregrounds. But for the small aperture telescopes, we only have one optics tube looking at these lower frequencies around 30 to 60 gigahertz, and then one higher frequency tube looking at from 200 to 300 gigahertz to 20, and then 4 or 5 small aperture telescopes looking at this bands. So that's one thing. The other thing that we need to think about when we make an instrument is the optical throughput, which is a very fancy way to say that we can be so noise dominated sometimes. And if you look at an example, this is the Helium power spectrum from the Planck latest release. And so if we were to zoom in at this subplot here showing the 1 sigma error, with this blue lilac curves, so it's wavy curves, then if we were able to control our noise and our somatics and so on, we should only be limited by the cosmic variance, which is hard to give a concrete definition, but it is what limits our ability to see a bunch of independent modes. Why? Because we cannot look at the sky all the time. So when we do the spherical composition, we don't have a complete basis anymore, a complete orthogonal basis. And then we have all these different angular modes mixing with each other. And it's also the fact that we're imaging the universe from, you know, one patch. So it's like trying to construct an object only from a single snapshot of a part of it. So we're very limited with that. Our natural defense against that is to try to increase the optical throughput. So this is what defines the number of independent radiation modes that we have propagated through our telescope for some radiation of wavelength lambda. So this optical throughput that I'm referring to is the product of the effective area of the telescope and the telescope solid angle. So, you know, when we talk about solid angle, is the 3D analog of the classic dimensional angle as extended to the sky. So what we call, which I guess most of you have heard, telescope's field of view. So our natural defenses against the noise is to increase as much as we can the number of detectors and look at the sky as much time as we can. So sometimes we need to go up the number of detectors like crazy. Modern telescopes have thousands of detectors in every array. Because if you were looking at a bolometer, let's say, see here. So this is the bolometer that we have fabricated in the University of Tokyo for the Science Observatory telescopes. And this is designed to operate at 100 million. And this is a ground-based experiment. So if you look at this nice cartoon that my supervisor made, I think it was a good idea because sometimes cartoons are the most efficient way to understand things. So the most signal that the bolometer will get is going to be from the instrument itself. And then we are unlucky enough to look from the ground, so we have the atmosphere emitting quite a lot. And then only a small signal will actually be the same signal that we indeed try to measure. So this is just a simple visualization to show, how many detectors one might need to actually get a lot of measurements and bring down the answer. So we need more detectors, more sensitive detectors. Once we do that, and we beat down the noise floor, then other things start to arise. And those are problems that were always there, but we just couldn't see them anymore because we had bigger problems. And this is a classic story as we evolve in instrumentation. So we have many systematics from the instrument itself, electric, thermal, and optical, which I have dealt most with. And in order to understand, how we're going to look at it in terms of the analysis that I described before, basically you have some expectation, some forecasted expectation about your remote signal. This is from the BICEP collaboration. It's not important to go through all curves, just as a visual aid. So you have this dashed red line, that this is supposed to represent the remote signal that you expect based on whatever priors and models you rely on. And then all those are optical systematics on the left panel, but what I want to focus on is that they have this green curve here, which shows what happens if I don't project all the systematics, if I don't, if I just ignore them and say, my instrument is perfect. And then you can see that this totally masks the remote signal that we're looking at. And from that, we cannot infer at all any values for the parameter that we want. This cannot lead to a so-called detection, not even to a constraint. So we need to be very careful. And the main category of the optical systematics is the beam systematics. That was the most long introduction I've ever done to introduce what I do. So this is the beam model part. And when we talk about a beam, we mean the instrument's response to a point source. And this is what defines the resolution of our instrument, the angular resolution. And well, the resolution, as you know, is the instrument's ability to distinguish between two separate nearby objects. And this is very much limited by diffraction. Now, diffraction will occur when a wavefront propagates through a slit or an aperture. And this is due to the fact that the wavefront will not propagate as a simple straight line, but instead as a bunch of spherical wavelets. And when those spherical wavelets encounter the aperture, then they're going to be diffracted and they will interfere in constructive or destructive ways and form complex patterns. If we have a circular aperture in a telescope, which is a very common case for the same big experiments, then the resulting pattern will look a little bit like this. This is what we call an airy pattern. It can be described by an analytical expression that relies on the Bessel functions of the first kind for a basis. So this pattern here is comprised of this central bright maximum that we refer to as the beam main lobe, and then this concentric dark and light circles that we refer to as the beam side lobes. Oops, there. And to the best of my drawing abilities, projected onto one beam. So this is one beam up, as we call it. So essentially, there is some function there that assigns one value at every point around the point source to some radius that we choose. And this is how we map the beam to the sky. Hence we call it beam. So this is a nice looking beam. Beams don't really look. And to support the statement, here's a selection of my favorite beams. That is what we used. So in the left panel, we have the WMAP beams as they were measured. So this is a satellite that I showed also before for the same experiments. And those can be rather elliptical. They don't resemble this nice spherical pattern that we showed before. And they have also this nice spillovers here. So the beam is leading outside of what we would expect the shape is. And that can be problematic for the test. Now for the COPE satellite, also very powerful experiment, for the Derby instrument, they actually used a square aperture. And I'm pretty sure they had reasons for that. However, this is an analyst's help when you try to decompose this kind of beam, with these sharp edges from your angular spectrum and your maps and your data. So decisions like this, like a square aperture, should be taken into account when you try to decide what kind of modeling you want to do with your beam. If you go to simple, for example, let's say that we have the previous beam here, and those little bumps, those side lobes, they're not little bumps anymore, but instead, let's say that they carry some significant power. But somehow you decide to model the beam as a simple Gaussian, because that could be a choice by just looking at the shape. Then you might just end up with residuals that look like this right panel on the side, which popped up on my computer. It was also my first or second year of PhD, so there was serious thinking about changing career there. But my point is that if you ever see this thing popping up to your computer, you have done something wrong, you have gone to simply just close your computer and run out of the house and get a beer and start over the next day. So we need to be very careful when we do wrong. And as you can see from all these different things, we don't only care about the resolution, but there are a bunch of other effects that can mess up our analysis. Just want to check the time. Okay. So, as we talked already for the side lobes, for these little bumps, if they are powerful enough, and if they're very far away from the center of the beam, might actually pick up parts of the sky that you don't really want in your data. So let's say that you want to avoid the galaxy, because it has these contaminants that we talked about that are very strongly emitting polarization. But then you might actually pick up some of the signal of the galaxy, and this will be an additive effect to one of your clean pixels, one of the regions in the sky that you don't intend to mask as aggressively, and you hope to get contour strains from there. You can have the beam be symmetrical, as we saw before, and this will propagate some degree of ellipticity. And if you don't correct for that, your temperature will actually start leaking into your polarization data. And since the temperature is so much stronger, this will be quite problematic when you try to use this polarization data to clean them even more and get the faintest signal that we are after as a community. And then, of course, there is a dreadful case of your beam non-idealities just strolling around your telescope and going to become buddies to imperfections from other optical components, such as the half-wave plate, which is a polarization modulator that we also commonly use in SIM. And now we have looked at that a little bit with my group in Stockholm a couple of years ago, and it turns out that this coupling is so strong, happens in additive ways, in multiplicative ways, and it's really, really hard to calibrate out. You're going to see this effect rising over your desired beam mode spectrum. Now, we map all these effects into these beam maps that I showed before, and another convenient way to do it is that we take the harmonic transform of those beam maps, and we call that the beam transfer function. And if we were to plug this in the formalism, just to convince you that it is something that acts directly on the spectrum, let's say that you have measured your spectrum, which is what you denote there with this tilde on the top, so the left side of the equation. So those are the measured spectra of the sky. And then those will have to be linked in some way to the true spectra, which are the CLs without the tilde on the right side of the first term. And you need a bunch of factors to connect these two, because your instrument gets in the way. And so you have just in this basic formalism here, series of factors, you have this M factor, which is called the mode mixing kernel. And that, in fact, gives you an idea about when your basis orthogonality breaks, mostly due to cut sky effect. So when these independent modes that we talked about before start to mix, and then you lose accuracy and robustness in your analysis. And then you need some way to quantify all the filtering that you did to mitigate the noise in your data, and you do that with this so-called filter function BL. And then the beam window function BL that we talked about just now, this acts directly on what you think are your true spectrum. And then, of course, you have a noise term to complete the whole. So every experiment that has been deployed or is going to be deployed has dedicated at least one section, one powerful section in some paper to show these beam transfer functions that they measured, they reconstructed. As this example of the ACT telescope publication, the recent one in 2021, where they did their beam reconstruction based on Uranus simulations. And now I'm going to talk about what we do as a community to model these beams, but it would be maybe a good time that I take a sip of water and tell me if you have any questions. Or if you're still alive, I haven't made you dizzy enough. I can still go on. Okay.
Can I ask?
Yes,
what
please.
is the special resolution that you aim for?
Well, that depends on your scientific goals. So, for example, in a very simplistic way, the beam resolution, the beam size, if we quantify it in terms of the WHM of the Gaussian, then it will allow you to go to a multiple number, not exactly, but let's say roughly 180 to this L number divided by this beam resolution, right? So if you have a half-degree beam, as is the case for the mid-frequency bands for so, you can, plot. You can look at amplitudes up to, well, sky effect side, 360. So if you want to look at beam modes, you want to focus on the multiple range where you can track each effect from in the power spectrum. So the beam modes, we think that they peak around a multiple number of 80. So I need a telescope that can be very good at tracking this range of multiples. Now, for the large aperture telescopes, wants to look at lensed beam modes, so these E modes that were masqueraded. So what they were doing is that, where am I? I have a lot of slides. Okay, good luck to you guys. So what they're doing is that they want to look specifically at the higher L multiples. So for that reason, they have a different beam resolution. So your beam resolution needs to just be able to track the multiple range that you want. So you have to decide based on the scientific goal every time. There's not a trivial. It depends on what you want to visualize. But that's a really good question.
What about the Simons Observatory?
So for science,
Beam mode,
yeah, for the beam modes, we actually have beam resolutions that are close to half degree for mid-frequency bands, just to track this part here very well. And the large aperture is actually like 1 or 2 arc minutes is the beam size, so it's just we want to go very, very high. And also they're going to do some galactic science in theory with the lab. So okay, thank you for the questions. Actually, that's really nice. It was okay. Yes, so we want to get this thing. So we want to reconstruct our beams somehow and get out a beam product that we would use for the analysis to see how much we manipulated the data. How do we do that? On the field, we have natural choices, we have astrophysical sources, especially if we have a satellite, sources to kind of fly around you. From the ground, things are a little bit more difficult. And when the astrophysical sources cannot be in line with your calibration requirements, then we employ man-made sources. Of course, we need to have some level of preparation in the lab. We're doing near-field measurements. We're doing, well, that's kind of an old technique, but recently we have approached the beam reconstruction of the Simons Observatory beams in the lab in a holographic approach. So that's kind of innovative for SIMB telescopes. I think, if I'm not mistaken, I'm solving an experiment in the past, but I don't think it has been done for SIMB telescopes before. Okay, so most of the SIMB experiments, not all, but most of them have at least used astrophysical sources in the past to do beam calibration, or at least subsequently to some other artificial source. And those are natural candidates. We have also the moon, if we want to map the far side of the beam, so the power very much away from the center, because it's massive, it's up in the sky every night, it's very, very bright. And they have actually succeeded in doing this beam reconstruction of the far side loops for the class telescope. But there is a small trade-off. So because it is very bright, it can actually drive your detectors nonlinear. What that means in practice is that you might still have incoming power in the bolometer, but then this signal just reaches a maximum and doesn't register any additional signal anymore. And so this is what we call the saturation effect. And if we have time, I can just say a small little, yeah. So you can think of this way. You have a glass of water, and you want to measure water with this scale. And you start putting ticks at 100 ml, 200 ml, 300, 400. So when you start pouring water, you're going to see when the water reaches 100, 200, 300, 400. But if you exceed the half-liter capacity of your glass, then the water will just start spilling out. But to your eyes, if you're only looking at this glass, you still have half a liter of water. How do you get rid of this problem? Just empty your cup of water. Look away from the bright source that is saturated. But there's always this trade-off there of how much this saturation will affect the calibration that you do, which is a statement about how sensitive your detectors are, so how easy to be messed up. Okay, so we have planets and so on, but we also observe from the ground quite often, and planets are not going to be always visible from everywhere above the horizon. So if we're looking at Jupiter, that is a natural candidate that has a high signal to noise ratio, Then for this fall, for example, that we're doing some initial observations to calibrate the SO telescopes, well, Jupiter doesn't rise higher than 50 degrees. And the atmosphere there is very problematic. So, also not all planets are bright enough to calibrate the beams of the telescopes. We were looking at Saturn, let's say, and Saturn appears to be kind of under the noise, or at least we haven't cleaned up the noise enough. So for dim planets, those can be masked by atmospheric signal and by other types of noise in your telescope. And the everlasting problem that the astrophysical sources are not, the planets at least, are not fundamentally polarized. So you might go up as to 3% of polarization fraction, I think, according to some Planck studies, the latest ones, but they are fundamentally unpolarized. We have tau A as a natural candidate in the sky, and ABS has done the calibration of the polarized part of the beam on tau A. But the problem is the following: if you have a very wide beam, so let's say this half-degree resolution that we talked about, that's 30-minute resolution, tau A has an optical length of 5 by 5, which means that we're going to visualize tau A inside our beam. But this area, we're actually going to have it full with diffuse emission. And what you can do after is to try to separate those two based on their signature on the spectral energy distribution, which is not exactly trivial, but I think it can be done. Anyway, it worked for them in tau A, so that's also a candidate there. However, due to all these problems that come together with astrophysical sources, we have built a natural defense in terms of making these sources of our own and try to propagate them at a distance far enough from the detectors, so for our instrument to still be able to perceive them as both sources. So in the case of BICEP, on the field, they actually mounted the source on a very tall tower, a very tall structure, and they did the calibration like this. Another thing that happened, which was interesting, was that in the boomerang experiment, that was a balloon, they hid a source behind one of the mirrors. And this source was flashed at fixed time intervals to do the calibration of the instrument. Another innovative idea is to have this ambitious space-borne open access calibration source for both suborbital and ground-based experiments, but this will take a lot of time and money, I think, to construct. So what we're actively looking at as a community and for us all is to mount the source on a drone and then just fly this drone over a telescope to do our calibration runs like this. And we actually did that, we tested that, and we got very good signal-to-noise ratio. And this is because we can actually tune the signal-to-noise ratio of a man-made source. We don't have to rely on the natural brightness of the astrophysical sources at the moment. We don't have to wait for the astrophysical sources to be apparent. We can fly the drone whenever we want. And we want, to calibrate the polarized response. We just put a polarized grid in front of the source. So those are all great merits of the drone. We have technical constraints. It needs to be powered all the time. It needs to stay stable for some time. And we have constrained this to be about 12 minutes of flight. We're super safe when we're only flying it for 12 minutes. It's stable, it's powered, it's perfect. And the question is how many of those we can do to meet our calibration requirements. So one thing that we checked here, this is a pure power comparison from some work that we did for this book. So we're not assuming any simulation, any emission, nothing, just a pure mathematics comparison power. And we have looked at the power coming from planets, the SNR coming from planets, with Jupiter, of course, being the brightest, and then the corresponding SNR we expect from the drone. And as you can see, this is not only much higher, but it's also much flatter across the frequency range that we are trying to calibrate our beams. So this is why this is a very promising company. How much time do I have? I feel like I'm talking. And I tend to do that. Make 4 more minutes. 4? 5. Okay. Yeah, I can do that. Okay. So, and now we're in the lab. So now we're in the lab, and we are using thermal sources, and we're doing measurements of battery. And those, they can only keep amplitude since they have black body emission spectrum. They don't have any phase information, but they are very useful. To track intended reflections of the beams, what we call as ghosts. So those are the beam maps, but of course they don't look as perfect as the pictures that we showed before because they're in real conditions in lab. And those are constructed for a detector at the center of the focal plane, which in theory should give you the best beam maps that you got because it's fully symmetrical image. And even here, you can see that there is this really bright pixel here. This is a nice beautiful ghost, which can be dangerous if not, modeled or tracked at least before. And then if you go to the edge of your focal plane, you might actually have the focal plane being illuminated asymmetrically. And this will result at some degree of elasticity of your beam, which, as we said, can be also rather. So we need those measurements to give us an idea, to give us future references about how to construct our optical setup better. And then if we go to the last category, which is the holography we talked about before. So this was recently pioneered for CFB experiments, if I'm not mistaken, again by Dr. Grace Chestnut in the University of Chicago. And what she did is that she took coherent sources instead. So now we have phase information. And we actually do these measurements for single frequencies, not frequency bands anymore, because we have phase information. So we choose a number of single frequencies around every band that we want to map, let's say the 9150 bands. So that means bands centered at 9150 gigahertz. And then we do these measurements. So how do we do these measurements? If this plays, it's going to be very interesting, but it doesn't play. This was supposed to be a video. Okay. Yay. So this was done by Grace. It never shows at the University of Chicago. So she has the coherent source. And you see here the focal plane, the tube that hosts the lat receiver, the lat aperture receiver. And then the source just goes mapping in different angles on top of the detector, which was, one of the most relaxing videos you can ever see if you're doing beam modeling. It's just so nice. And it happens eventually. So you see this beam map, this real condition beam map forming. So it's not pretty at all. It has a very pretty spillover of power here. But, it can be a problematic map or something that you need to model at least. So we got a bunch of those big maps, and you're doing that at this measurement. So now you need to be able to propagate this in theory on the sky, so away from your telescope. So what they do is that they have the instrument, and then you have the beam maps on this plane of the instrument, and then you simulate the source very far away. And the fields from the source come to meet these fields that we measured, and you multiply those two. And this is a way to propagate the amplitude and the phase on what we call the far field, so far away where you're going to actually measure your astrophysical sources. So this is what we got, and those look quite good for the middle frequency bands, the bands that we have the most hopes on constraining the scalar ratio. Well, kind of. And then you bring those radially, as is common when you do beam analysis in terms of delivering beam products, and you compare it with simulations. And as you can see, those are in very good agreement for a method that is as new and as innovative and in real conditions. So that's definitely something that will be done again in the future, and we're doing also for the small aperture telescopes, but those are not public yet, but they will be soon. I'm not going to go into much more because we don't have time, I promise. Just one last thing, that for the simulations, yes, we do all this work in the field and in the lab, but we need to have something to compare with. And we do that by using, advanced optics softwares. Let me kick this thing out. Whoop. In my group, we use Dachlythra tools, and this relies a lot on the physical theory of diffraction. So we go and build this little cute toy telescope in here with lenses and apertures, and we start doing what we call ray tracing, which means that we propagate the rays from the focal plane, we do it in tiny size, through the lenses, through the aperture, and onto the sky. And here, at this point, is where we expect that we get these beam maps that we showed before. So those simulated maps. And yeah, the specific one is for the 3-lens refracting telescope set up for the Science Observatory small aperture telescopes. And this is what we do as a total of the community. And I'm not going to show the next slides because we don't have time, but we can. I'm just going to go to the summary for whoever is still alive. So yes, we need to calibrate our beams properly. They can really mess up our cosmological analysis. We do everything that we can to do that. Astrophysical sources, artificial sources, holography, near-field measurements. We model our beam in terms of beam maps, transfer functions, whatever is the most convenient for our cosmological analysis. And it's really, really important to just take all the beam biases that we find from our simulations, from our lab measurements, and quantify them in terms of the forecasted accuracy of the gesture scalar ratio, if we are, in order to just be able to, meet the ambitious angles that current and next single telescopes set. And I promise to leave you alone now, so thank you for listening. And sorry that I cut my out.
Thank you, Nadia. Any questions from that? Nico.
Thank you for the nice talk. I will go back to the beginning for this. You talked about lens beam modes.
Yes.
Can you elaborate a bit? Where do they come from, basically?
So, when you have the semi-focused property of the universe, then you have the path of the light being distorted, and you have gravitational lensing when you have massive objects. So this will actually induce some mixing between the two parts of the polarizations, right?
Because so you mean the polarization plane of the locomotive wave will be rotated because of
Exactly.
but this, as far as I know, only happens in relativistic spinning sources. The sources that are spinning.
I will not claim that I know more about lensing because I have never
Because I
done more yet.
didn't hear about lensing.
No. There are. That's a very important part. So this is what we're trying to look at with a large aperture telescope. I can talk to you about the instrument side of things, but we can easily figure that out soon. Actually, haven't reached base with that part of cosmology for quite some years. But the idea is that yes, because you perturb your polarization plane, then your remote and remote effects become mixed. I'm pretty sure that we can, put our heads down and find a mathematical formulation that leads to that, but I'm not going to pretend that I have this.
I'm guessing since these photos come from the Stockholm University, there must be some relativistic speeds related to section. Okay.
Yeah, I don't want to say something that is not going to be accurate. I have a thought about this, but I don't want to confuse anybody.
Any more questions?
Yes.
But it will be difficult to separate the ISM polarization, like program polarization, to detect this beam mode and
For the lensed ones.
yes, like in the previous slide.
Yeah.
So this is something simulation or it's a real thing?
So this is just like the, just the schematic of the expectation, some of the W mode.
So these vectors are like observed one or
This is the pattern, the most simplest pattern that you can visualize in the polarized field on the sphere. So this is mostly like curl free, and this is divergence free. It's a very simple schematic. It's just to show some context. The problem with the foregrounds is that they produce also strong beam mode polarization. So that's how you use them to separate these parts from the CMB. So the CMB has only beam mode is strong, and the beam mode is the very faint primordial signal. He looked at, like, this is only for the CMB, right? So this is much more stronger than what we expect from the beam. The problem with the polarization for the foregrounds is that they also have strong beam modes. So those are going to be very, very much masked. But another thing that you can do, and I'm guessing you know more about them, but is to use the correlation between A and B. So the foregrounds will have that to some degree, but the CMB is not expected to have correlation between A and B modes. So you do all this kind of fancy stuff when you do foreground component separation. But again, I'm pretty sure there are other people that know more about this in this regard.
Any other questions? In the audience, maybe? Online? No? Sorry.
Okay, so question, once you understand your beam mode, what do you do about it?
That was the last slide. First of all, you learn how to give a talk in the time that people assign you, I think. Okay, so that's exactly where I wanted to get. So, you're going to decompose that beam from your sky signal. You might do that in the map domain, which is not most more complicated. But let's say the simple version here that you have the measure angular spectrum, and you just divide it out. You divide the symmetrical part of your beam out, which is going to be here the strongest part. And then you need to have some foreground component separation algorithm, and the map-based, power spectrum-based, you just pick your favorite as a collaboration in this, and some priors, you know what you expect from the sky, and use all your knowledge from the instrument. So put all the instrument parameters that you measure. And this will give you as an output, typically, some estimation of what your foregrounds are, your contaminants, how those can be modeled efficiently to be discretized from your CMB. And then it's going to give you hopefully some representative mass spectra and some systematic residuals that are going to be hopefully low, and eventually the clean spectra that you will use for the cosmological analysis. And this might just look like a very short, simple bias that will not affect you at all, but this is why I wanted to have a little example that I did as an exercise. And If you take the simplest case, a Gaussian beam, a half-degree beam, again, same test case always 9 gigahertz. And let's say that you perturb this parameter, you just perturb the beam size. And you take a set of 100 simulations to also have representative covariance of your sky. You take 4 such sets. And for each simulation of each set, you start drawing a value for this WHM from a Gaussian distribution that is centered on the true value and some statistical uncertainty of half, 1, 2, 3 arguments. So you go from a bias from roughly 1 to 10% of the beam. And then, well, I'm not going to go into those parameters better than me, but just focus on, let's say, the length and amplitude and potential scalar ratio in some easy model with simple sky, no peculiarities in the foregrounds, no standard deviation in the spectral length, nothing. And well, you feed all that to some foreground component separation, and you get out some likelihood to the parameters. And then you see that my true values here in A-lens and the tensor scalar ratio that were supposed to be 1 and 0, then even with a 1% bias of the beam size, you can get as much bias on the output value of the lens. It doesn't affect the tensor scalar ratio so much. That's like 10 to the minus 4 of uncertainty, and modern experiments are kind of constrained this constraint. So that's fine. And again, this bias, you know, it's purely driven also by the sample conditions that we put in our foreground. The same thing. If you had more complicated models, this could be even masked and have bigger problems, but there is a direct link. So that's my point here, that what you want to do at the end is that you want to do the best to reconstruct your beam, and then go and plug it in an analysis like this, and go and check directly, what does it do to my parameter? What does the beam size variation, the ellipticity, everything that you can think of that can go wrong with the beam needs to be quantified here. And if we were to perturb also the high frequency beams, for example, maybe we would see effects on the spectral foreground parameters as well. So yeah, I'm sorry, I know this part was really important. I'm sorry I didn't time it. I get the what do you do after question.
A follow-up question. What do you do to test for the stability of your beam? So you have a model of your PSF, right?
Yeah.
But you have moving components in your telescopes.
Yeah.
And as I understand it, at least the Simon Observatory would be actually pointing at different parts of the sky, right?
Yes, but you start, I guess that depends on how you do your beam calibration at the beginning. So the strategy that you choose, you do like elevation scans, you try to fluctuate the strategy, the least amount that you can. You just try to circle a little source, get enough signal to noise ratio, and get out of there. Kind of, you want to get the most stable conditions that you can at beam calibration, and then people have checked. I know for previous experiments in the past, the time response of the beam, and it wasn't, way too radical. But I guess you just start by doing the smallest movements that you can, and you have this beam. And then, of course, you can actually get, what you're talking about. I think it's what people call instrument beam, probably. So at this part. And there are methods to do that at the map domain after you have your formation. But that gets much more complicated.
So how often do they plan to calibrate in DSO?
Yeah. So we have these different stages of deployment. There are lots of logistics there. So the first calibration was going to happen last week. We had a small cooldown problem. So next week, in theory, data comes also at my computer at like 2 a.m. at night, and we do the first calibration of that. And we're going to do that using the moon for detector pointing, and then for Jupiter's flow. So we're going to use Saturn and stack a bunch of observations from the beam response. So that's going to be to get some initial numbers. And then I guess when we start like the early, just first light.
I mean, during science operations, right?
That I don't know.
How often do you plan to go back to calibration?
I don't know. We were supposed to also have commissioning for a couple of weeks. I'm not entirely sure
Okay.
how the structure is going to work. I think like you're going to have what people call 2 cycles of science. So you're going to do before the science observations, we're going to do one more calibration run, I think, for a week, but those are a little bit fluid. Then you're going to have what they call 2 mission cycles, but those are ranges a little bit. So first you're going to do small cycles to make sure that you control all your systematics and your analysis. And then after you're sure, you're going to start expanding. So eventually, like after you change something on the science cycles, is the idea that you do one more calibration from those cycles, and then the next, and from the next. But yeah, it's,
All right, if there are no more questions, let's thank Nadia again.
Thank you.